Hi, Rodrigo.
Hi, Rodrigo. One sec. So, 1 second. I'm just waiting for the YouTube now. Okay, here. Okay. So, no, what is okay. So now you are co-host. Okay.
Okay, thank you.
So just 5 minutes to have everyone coming in, and I have to.
Okay.
And how is the situation in Barcelona? It's back to school, campus.
So all the teaching at university is online, except for first year courses. And but recently they started to, except for first year courses, and also for degrees where you have to do some practice courses. So these are in person. For the rest is online. But it seems that now they are allowing even courses for second year courses and also third year courses. Some of them they start to be in person.
How is the vaccination?
Vaccination is still low. It's around 20%.
Ah, yes, like you.
but at least is the oldest people. So now they are the vaccination is for people who are over 60 years old. So which gives you like, even it's only 20% of the people who receive the first shot. Well, since it's the most vulnerable people, so and now it seems that the number of cases is decreasing. So now we are in a good spot, although you never know how it's gonna evolve.
Yeah.
How about here?
Well, here it's also 20%. We have a smaller, I mean, the number of older people is less than the one in Europe. So they supposedly, at least in Rio, they vaccinated people above 60, but because they're less. And they vaccinating people of working in hospitals and so on. And they started vaccinating people at the university, but then they stopped. So yes, at the same time they want us to go back teaching presentially, but you know, it's unclear how this could be done, because you know, if you're not vaccinating people, and and it's not just the university, it's going to the university. Some people have to take a lot of transportation.
Public transportation.
And they're very public transportation, very crowded, so it's highly, you know, risky business. So this is the this is the problem. So yes. So I almost 1 second. I cannot do 3 things.
It's very difficult to.
Yes, I'm sending the link to the YouTube.
Yeah.
Okay, almost done. Okay, done. So sending to. So okay, so I guess we could. We ask everyone, please, to identify themselves with the full name. Yeah, so, since we are all here, we don't see everyone, but at least we do recognize the name. So it's so please, if you don't have, hi, Owe, I haven't seen you getting in.
Hi, Stefanella. How are you?
Hi. So we are people from Pennsylvania today. Very happy. And your contribution, because we have Sweden, we have Barcelona. Nice to have you.
Good to see you. It's been a long time.
Yeah. So we are all physically restrained, but at least we can travel with the mind, as to say.
Não sabia que era para isso que eu tinha imprimido. Achei que você botar só no saquinho junto, sabe?
Okay, so asking people, please, to not the speaker, obviously, to close the audio, just the audio. You can. It's still nice to see you. So, okay, I think that we could start. So, Rodrigo, where are you? Is Rodrigo there?
I'm here.
Yes.
Okay, so I'll start recording. And okay, so it's very nice. This new mini course, very nice to receive someone from the group of Barcelona, second family to me. So I let our co-organizer Rodrigo from Sweden to introduce Gemma Huguet. I hope I pronounced it correctly. So please, Rodrigo, the floor is yours.
Okay, thank you, Stefanella. So today we have the pleasure to welcome Professor Gemma Huguet. Dr. Huguet is Associate Professor at Universidade Politécnica de Catalunha. She was postdoctoral fellow at the Centro de Recerca Matemática and New York University. Her research line is computational neuroscience. And today we will have the first lecture of her course, Introduction to Mathematical Neuroscience. So please be welcome, Gemma.
Thank you, Rodrigo, and thank you, Stefanella, for the invitation. I'm very happy to participate in this international school on dynamical systems and applications. And as you said, this course is going to be about mathematical neuroscience. I'm just going to give you an overview or a little taste of the field. Okay, so to start, since this is the first session, I'm going to start with an introduction to this field. So what is computational neuroscience, or what is mathematical neuroscience? Well, this is a discipline that wants to provide quantitative tools and methods for characterizing what nervous systems do, determine how they function. So we want to know how, we want to know the mechanisms, not only what they do, but we want to know the mechanisms. And we want to understand why they operate in this way. Okay, so how do we do this? Well, this is a very interdisciplinary field, because these quantitative tools that I'm talking about are tools from mathematics, from statistics, from computer science, from physics. So these are the tools that sometimes are under the name of STEM disciplines: science, technology, engineering, and mathematics. And how do we use these techniques to understand the brain and to understand the nervous system? Well, we need to interact constantly with experimentalists and with data, and we need to work with data from experimental labs. To do what? Well, to fit and interpret the data that are coming from the experimental labs. Then we can test hypotheses using our quantitative methods, and then we can make predictions and suggest new experiments. Okay, so this is a little bit the goal of this field. So what is our object of study? Our object of study is the human brain. Actually, we want to understand how our brain works to perform the task that we do in our everyday life. But this is a very complex organ, in the sense that it consists of 10 to the power 12 neurons, which is the basic unit or the basic cell in the brain. But each of these neurons can communicate with, on average, with 1,000 neurons, other neurons. And this context, this between neurons, which are called synapses. So in our brain, we have a number which is of the order of 10 to the power 15. So you can see the complexity of this organ. Then, if we want to study it, we need to decide at which scale we want to study it. Okay, so we can study the whole body, the whole brain, treated as a whole, and this is possibly the approach, or like the object of study of psychology. And but then we can decide like to look at a particular region or a cortical area. Let's say we know that vision is associated. So when we perform a visual task, then the visual cortex is involved. So then we might focus also on this big region of the brain, which is in our back. We can also go a little bit deeper, and then we can study at the level of circuits. Circuits involve like thousands of neurons connected. And this is a local network. And we know that this is the basic unit for which we can correlate the behavior observed at the level of the circuit with cognition or cognitive tasks. Or we can even go a little bit deeper, and we can just restrict to the cellular levels, just to study what the neurons do individually. Or even we can do a more detailed study and look at a subcellular level, and then we're going to study channels, receptors that are involved in the neuron. Okay, so you can see here that there are several scales, and then when we want to approach our study, we need to decide at which level we're going to study the brain. So for this course, and basically because this is where I did most of my research, I'm going to focus on the cellular and circuit level. So I'm going to start first talking about the physiology of the neuron, of a single neuron, and then I'm going to move to a higher stage, which is like connecting several of these neurons, creating a local network, and study the behavior that emerges in this network. So how do we do this? Now I already said what is the level at which I'm going to study the brain. So, but what are the math tools that I'm going to use? Well, as I explained at the beginning, there are several approaches to study the brain, and there are several math tools that we can use. For instance, nowadays the labs are producing a lot of data. Therefore, so all these tools from data analysis, statistics, information theory are going to be useful to understand the data that are produced in the labs and to extract patterns from them. As I said, also, the brain connects, like neurons are connected. They have many connections between themselves. So we can look at this structure as a graph, and then study it with tools from graph theory or topology. And another math tool that is very useful and has been used a lot are the differential equations. So try to describe the variables, the evolution of several variables by means of differential equations, tools from dynamical systems, etc. So for this course, and because this is my area of research, I'm going to present an approach based on tools from dynamical systems. Okay, so I'm going to focus on this. Okay, so as I said, what I will try to do over these 4 sessions is to go from the description of models of the dynamics or the description of a single neuron, okay? And basically, I'm going to present the classical Hodgkin-Huxley model, and then we are going to see how these models are going to be simplified to be integrated in a network for which we are going to establish connections between neurons, and we are going to study the macroscopic dynamics that emerges from the network of neurons. Okay, so this is the idea of this mini course, is to bring you from the description of the dynamics at the level of the single cell of the neuron to the dynamics of a local network or a circuit, okay, which involves like thousands of neurons. So this is the outline for these 4 sessions. Today, what I'm going to present you is the dynamics of the membrane biophysics and the Hodgkin-Huxley model, which serves to describe the dynamics at the level of the neuron. On Thursday this week, we're going to study these models, and we're going to study the excitability properties of the neurons. And basically, we are going to do it using tools from dynamical systems theory. So we are going to do phase plane analysis, and we're going to see a little bit of bifurcations that these models undergo. And then the last 2 sessions that are going to be next week, I'm going to talk about the dynamics at the level of the network, okay? And for this, I'm going to introduce what is called the firing rate models and some famous set of equations, which are called the Wilson-Cohen equations. And for the last session, I'm going to present you an application of a model that describe how we take decisions. So what is happening in the brain when we have to take a decision? Okay. I haven't said it at the beginning, but please interrupt me if you have questions or using the chat. So or stop me if you want me to explain something slowly.
There are some questions on the chat, but we thought maybe you answer at the end, as you wish. As you wish. There is.
Okay.
If you want, there is one now. Do you want?
When I talk about, well, this is an estimate using data from experiments. Okay. So basically, it's just looking at the density and then extrapolating. Okay, so for the session today, I'm going to start explaining the membrane biophysics and the classical Hodgkin-Huxley model to describe it. So the object of study for today is going to be the neuron, which is the basic cell in the nervous system. And the neuron consists of, let's say, three parts or three main parts. One is the cell body, okay? Then we have the dendrites, which are these parts here that they look like trees, and they are like the sort of the antennas of the neuron through which the neuron receives or makes contacts with other neurons. And then it has this long segment here, which is called the axon, and for which there is an electrical signal that travels along the axon till this axon terminal. And through this axon terminal, it makes contact with the dendritic tree of other neurons. Okay. And the object for today, or what we're going to study today, is this electrical signal, okay, that originates here in this initial part of the axon, and then propagates along the axon until it reaches the axon terminals. Okay. This electrical signal is called an action potential, and this is what I would like to describe now. So what do we need to know about the neuron? Well, we need to know the neuron is that the membrane of the cell separates two ionic solutions with different concentrations. And remember that ions are electrically charged atoms, okay? So this fact creates a membrane potential, okay, which is due to this charge separation across the cell, okay? And this membrane potential is what we can register in an experimental lab, okay? This voltage V that we define as the voltage difference between the interior and the exterior, okay? By convention, we assume that the exterior is at 0. So we define the voltage as this. So this is the variable that we can measure and that we want to describe, okay? Typically, a neuron that is not active, that is at a resting state, has a membrane potential which is around -60 or -70 millivolts. So this means that the interior of the cell is more negatively charged than the exterior of the cell, okay, at a resting state, okay, if this cell is not receiving any input. But this is what happens at the resting state. But actually what happens is that if you look at this drawing, is that this represents the membrane of the cell that separates the interior from the exterior. Embedded in this membrane, there are these channels, okay, that can open and close, okay, and they allow the flow of ions. And typically they are specific in the sense that there are channels that allow a specific ion to flow in or out through them, okay? The fact that there exist these channels and that these channels can open and close is what can produce movement of ions, and this movement of ions produces changes in the voltage, okay? And this is what we want to describe. The changes that these neuron, that the changes in the voltage that the neuron can experiment. Okay, so essentially, so this is another representation of the axon of the neuron. Remember that this, the picture that I showed you before. And as I said, this neuron, the membrane of the neurons separate concentrations. There are two important ions that play a role in describing or in modifying the membrane voltage, which are the sodium ions and the potassium ions. Let me go back 1 second. The sodium, these are the most important ones, the potassium and the sodium. And the sodium. And what happens is that at the resting state, the concentration of potassium is higher in the interior than in the exterior medium, while the concentration of sodium is higher in the exterior compared to the interior. Okay? And so we have that potassium is higher in the interior and sodium is higher in the exterior. What happens is that at the resting state, the interior is more negatively charged than the exterior. But then, due to, for instance, a brief perturbation that causes a change in the voltage, this may cause that the sodium channels open. Since the sodium channels open and the concentration of sodium is higher in the exterior, what happens is that due to this concentration gradient, the sodium flows in. And the sodium are positively charged particles. So this means that they cause that the membrane potential depolarizes, okay? And when this happens is that the voltage raises. What happens is that this causes the potassium channels to open. And when the potassium channels open, since the concentration of potassium is higher in the interior than the exterior, then what the potassium does, it flows out. And this causes the membrane potential to repolarize again, okay? And typically, the membrane potential shows this shape. So at the resting state, the cell is negatively charged, okay? Then at some point, sodium channels open and this causes sodium to flow in and this causes a depolarization, okay? So the voltage then becomes positive. This, when the voltage becomes positive, then the potassium channels open. And when the potassium channels open, potassium flows out. And this brings back again, it repolarizes again the cell to a negative value, okay? And typically, the voltage shows this shape. This shape, which is very characteristic, is called an action potential. Okay, and it's a rapid change in the voltage of the cell. And this is a change in the voltage. This is the change in the voltage that we're gonna see if we pick a point along the axon and we register the membrane potential at this point. But if we do this, At another point, we're going to see the same shape, but a little bit, if the direction is this, so we're going to see at each point, we're going to see the same change in voltage, but with a delay, okay, but later. So basically what we have here is a traveling wave. And this traveling wave, which consists of this rapid change in the voltage, this is the action potential. This is the electrical signal that originates here close to the cell body and propagates along the axon, okay? And this is what the experimental labs register in their, when they do recordings of a neuron. So typically, this is a typical recording from the voltage of a neuron. And basically what we see is that these rapid changes in the voltage here, and then periods where the voltage stays close to the resting state, okay? Every time there is, these peaks are called spikes or action. These are the spikes or action potentials. And if we zoom in here, what we see is this, okay, is this shape. When a neuron shows this type of spikes or this activity, or we say that the neuron is active. While when the neuron shows periods like this, we say that the neuron is at the resting state. Okay. I don't know if there was a question in the chat. Are these membranes usually elastic at normal force scales? Change migration with a membrane motion, membrane shape. Okay, if we want to model this membrane, so what I'm going to show now is a model to reproduce these action potentials. And what I'm going to consider is that the cell is isopotential in the sense that the voltage for all points on the cell is the same at the same time. Okay. But of course, you can go to more detailed models where you describe like how is the membrane, how are the dendrites. So you can put here a lot of details to describe like how is this action potential, how is this the membrane voltage for a particular type of cell architecture, okay? But for this course, what I'm going to do is next is something very simple in the sense that I'm just going to describe how we can generate these action potentials, assuming that the cell, all the points on the cell have the same voltage. So the cell is isopotential, okay? But of course, there are many more detailed models that we can do of a single cell. So now what I would like to present is the Hodgkin-Huxley model to provide a set of equations that are able to model these dynamic changes in the voltage, okay? So this is the model proposed by Hodgkin and Huxley in 1952, and this has been like so they did it for the squid because they were doing recordings of the squid, but of the giant squid, but this is a model, the paradigm, or like the mechanisms that are behind this model have been used, have become like classic in the field and are used to describe the dynamics of a single cell from there on, okay? So they did this work in 1952, and they got the This is a very important result, and they got the Nobel Prize for this in medicine in 1963. What I need to explain you what do you need to know so that I can introduce this model. So basically what we are going to do is like we are going to translate the neuron into an electrical circuit, okay? But first, let me explain you something. So as I said, the membrane of the cell separates two ionic solutions that have different concentration of ions. So for instance, if we focus on the potassium ions, we saw that the interior, the concentration of potassium is higher in the interior than in the exterior of the cell. Okay, so then what happens is that when the potassium channels open, due to this concentration gradient, what happens is that the potassium ions flow out, okay, in order to equilibrate these concentrations. But on the other hand, these ions are electrically charged particles. So they create an electric field. And what happens is that since the interior is negatively charged, what happens is that it pulls the potassium ions towards inside. So the electric field pulls the potassium ions inside, while the concentration gradient pulls the potassium ions outside. There is a value at which this reaches an equilibrium. Okay, there is a voltage value at which this reaches an equilibrium, where the concentration and the electrical potential gradients equilibrate. This is called the Nernst potential, or also the reversal potential, and is specific for every ion. Okay, and it's computed using this formula here. Okay, so it depends on the concentrations inside and outside the cell, and also on these constants. The R is the universal gas constant, T is the temperature, okay, and F is the Faraday's constant, and Z is the value of the valence of the ion. Okay, so as I said, this reversal potential depends on the specific, is different for each type of ion. So for the ions that are relevant to us, which are basically the sodium and the potassium ions, the reversal potential is around these values. So it's positive for the sodium, and it's between 60 to 90 millivolts, depending on the temperature and also on the concentration of this ion in the solutions. And for the potassium, the reversal potential is negative and is around minus 90 millivolts. Okay, this might be useful later to understand some properties. Okay, so now what I'd like to do is to translate the cell into an equivalent circuit model. Okay, so then we are going to treat the membrane of the cell, which separates charges. Okay, because it is let's say it doesn't it's impermeable to charges. We're going to treat it as a capacitor. Okay, and which models the ability of the membrane to store charge. And then the ionic channels, we're going to model them as a resistor, okay, which a resistance to the flow of ions. And actually, we're going to see that this resistance is voltage dependent, so it changes with the voltage. Actually, here I put the resistor, but actually we're going to taken more as a conductor, because we're going to use more the conductance than the resistance, which is just the one is the inverse of the other. And then this, and then we are gonna also consider that we have a battery which models the concentration gradient of ions. Okay, and the reversal potential is the potential generated by the battery. Okay, so the circuit, the electrical circuit, okay, that represents what the neuron does is this picture here. Okay, so we have the capacitor, we have the resistor, and we have the battery. Okay, and we measure the voltage, which is the difference between the interior and the exterior. Okay, so this resistor plus the battery built in series represents a specific ion channel. Okay, so then if we have several of these ion channels, so the circuit is going to look like this. So this is the capacitor that models the membrane. Then we have the sodium ionic channel, which is represented by this resistor and this battery. Then we're going to have the potassium, and then we're going to have this resistor here. This is represents channels that are not that are either always open. Okay, so it's not channels that open or close, but they are always open, and they are called leak channels or leak current. Okay, and let me introduce here some variables or some parameters. Sorry, some parameters that that are going to appear in the next slide. So the membrane potential is described by the variable V and is measured in volts. The current I, which is measured in ampere, and then the conductance is denoted by G. The resistance as the inverse of the conductance, and the capacitance of the capacitor, which is described by the parameter C. Okay. Now let's see how we translate this into equations. Okay, we're going to translate this circuit into equations. So let's see. We said that what types of currents that we have. We have the capacitive current. That is due to the capacitor. The capacitor are two conducting plates separated by an insulating layer, so it stores charge. And by Faraday's law, that says that the charge is the capacitance times the voltage. So when we derivate it, we have that the current, the capacitive current, is the capacitance times the derivative of the voltage. Okay, that's the capacitive current. And then we have the ionic currents. Okay, so this is the current through the channels. Okay, through each specific ionic channel, and this is proportional to the difference between the membrane potential V and the reversal potential. Okay, so by the Ohm's law, the current is the conductance times the difference between the membrane voltage and the potential generated by the battery, this reversal potential. Okay, this is just the Ohm's law. And finally, in these cells, we can also think that there is an external current that might be applied because it's the experimenter that applies an external current, or it's basically input from other cells. Okay, we're going to call it I applied. Then, using the current balance equation, the Kirchhoff current law, we say that the sum of all these currents must be equal to 0, okay? Or the sum of these currents must be equal to I applied, which is, or thinking that this current is negative. And then if we replace what is each of these currents, so we have that the capacitive current is given by this expression here, that we have here. And then the ionic current, so we are going to consider the sodium. Okay, we're going to put the expression for the sodium. So this is the sodium current. And this is the potassium current. And this is the what it's called the leak current, which is due to other charges that are less important. And we assume that this current is constant. We assume that the channels are always open, so that the capacitance, it is not that they close and open. So the capacitance is, so the conductance, sorry, is always constant. Here we're going to assume that this is always constant, okay? While the capacitance of the sodium and the capacitance, the conductance of the sodium and the conductance of the potassium are going to change, okay? They're not going to be constant, they're going to change, okay? So here, what we have obtained is an equation that involves the voltage and its derivative. Okay, so this is a differential equation. And this differential equation describes the evolution of the voltage. Okay. Now, as I said, this leak term is going to be considered constant. But these sodium conductance and potassium conductance are not going to be constant. They're going to have its own dynamics. So we need to write equations to describe these dynamics. Okay, so this is what we're going to do next. Okay, so these ionic conductances change over time, and actually they are voltage dependent, because depending on the values that the voltage takes, the channels open and close. Since the channels open and close, we're going to assume that in our equivalent electric circuit, we're going to think that the conductance of the conductor changes over time. Now, how are we going to model these changes? Okay, so we're going to assume that each of these the channels consist of different gates, and we're going to model the probability that these gates are open. So let's focus, for instance, for a moment on the sodium channel. For the sodium channel, we have a gate of this form, which consists of 3 pieces which are of the same type, which are these pink pieces here. And then this other piece here, which is different, okay? And in here, the channel is closed. Here in step number 1, the channel is closed. But then, if these 3 pieces, in this case, the 3 pink pieces are closed, but the other one is open. But the full channel is closed. But here, what we have is that these 3 pieces open. So these allow the flow of ions, of sodium ions, because this is still open. But then what happens is that, for instance, this piece closes, and then the 3 pieces close, and this opens. Well, in other words, we have 3 gates, the pink pieces, that are of the same type. And the probability that this gate is open or closed is given by the variable m. Okay? So m takes values between 0 and 1, which describe the probability that this gate is open. And then this other piece here, the probability that this is open or closed, is given by the variable h, which also takes values between 0 and 1, okay, and tell us whether this gate is open or closed, okay, or the probability that this gate is open or closed. For the potassium, what we're going to have is that it consists of 4 gates of the same type, and the probability that these gates are open is given by the variable n. Okay? And since it consists of 4 gates, it's n to the power 4. Now, we need to describe the dynamics for these probabilities, okay? For the probabilities that these gates are open or closed. So how do we do this? Let's consider, so the three gating variables are going to be modeled using the same equations or the same type of formalism. Okay, so let's call W the fraction of open gates. This W can be either H, M, or N. Okay, it doesn't matter because the strategy is the same. So let's call W is the fraction of open gates, or the probability that a gate is open. And then we know that, or we need to know like that the gates go from closed to open at a rate alpha that depends on the voltage. And the gates go from open to closed at a rate beta, which also depends on the voltage, okay? So then the rate of change in the fraction of open gates, or on the probability that the gates are open, so it's the same. The rate of change is given by the fraction of closed gates times the rate at which they become open. Okay, these go from closed to open. So this is the fraction of closed gates, and this is the rate at which they go from closed to open. And this is the fraction of open gates, and this is the rate at which they go from closed to open. So this goes with a negative sign. Okay, so this gives the rate at which the fraction of open gates changes. Okay, so notice here that we have an equation that involves W and involves the derivative. Again, we have a differential equation, okay, that describe the dynamics for the probability or the fraction of open gates of any type. It can be H, M, or N, okay? As I said, this rate at which channels go from closed to open or open to closed depends on the voltage. And so this, what we have here, that in the dynamics of the gating variables, voltage is involved. Okay. This expression here can be rewritten typically in this way, that in this form. Okay, where this function here, this is the steady state function, which tells us where is the steady state value. If the voltage is fixed, is that the steady state value that this variable tends to. Okay, and this is a time constant. Okay, at which this variable W approaches the steady state value. Typically, this function, this steady state function here, has the form of a sigmoidal function, a function that at plus infinity tends to 1 and at minus infinity tends to 0, or vice versa. Okay, and then so this typical shape here, or sometimes these are called also logistic functions, sigmoidal functions, etc. So the steady state function for the variable h is like this, And for the variables m and n are these ones here, m and n, okay? So this means that when the voltage is negative, low, what happens is that m and n tend to be close to 0, while h tends to be close to 1. And as the voltage increases, what happens is that m tends to approach 1, and n tends to approach 1, while h tends to approach 0. Okay? And the other ones tend to approach 1. Okay? And these are the time constants. That is how fast they approach this value, this steady state value. And notice that the time constant for the variable m is much smaller than the time constant for the variables n and h, especially at this range of voltage values. So this means that the dynamics for m is much faster than the dynamics for n and for h. Okay, and this is going to be important in future lessons, okay, because its time constant is smaller. Okay, so putting all these things together, the equation for the voltage and the equation for the gating variables, we obtain, so let me skip this, we obtain the Hodgkin-Huxley model. So what we have here, okay, this is the equation that we obtain for the voltage, imposing the current balance equation, just equating all the currents equal to 0. The capacitor current, the sodium ionic current, the potassium ionic current, the lead current, and the external applied current. So that's the equation for the voltage. Here, V dot denotes dV dt, okay? Which has this expression here. And now what I did here is I replaced the sodium conductance that I mentioned that it's gonna depend on the voltage by this expression here that involves the variables m and h, okay? And m,
Gemma,
yes.
there are some questions in the chat.
Ah, sorry.
No, I didn't want to interrupt.
Yes. Exactly. So I'm assuming that the voltage is only time dependent. It's not dependent on the position on the cell. So I'm assuming that the voltage for all points on the cell membrane is the same. Okay, it's isopotential. And the other question is like, could you recall the definition of the torus, please? The torus means this here. This is just this is the time constants. It tells us how fast this variable approaches the steady state value. Okay, and actually this time constant is also voltage dependent in the sense that, for instance, for the variable h, you can see that at values in this range, it's larger than if we go to higher values of the voltage. So it means that the dynamics here for h, it approaches the steady state much slower than for higher values of the voltage. Explain the define. Yes, if you want to explain, yeah, that's a good question. If you want, so as I assume that the voltage does not depend on x, okay. So if you want to consider that the voltage depends on x, so this is you need to add a diffusion term. So then you have a PDE, a partial differential equation, and then you need to add a diffusion term, okay? Because, and assuming that x models the distance along the axon, so if this is the cell body, This is the axon. So we start here. And then we have, okay. And then what we need to assume is that we need to add here diffusion term. And what happens is that you have a PDE, and for which the solution is a traveling wave. Okay, so then you can impose the ansatz for the traveling wave and solve this PDE. Okay, this is called the cable equation. But I didn't explain it here in the course, but it's also a very interesting. It's a very interesting topic to explore, actually. So going back to this model here, and just to finish. So putting together all what we have discussed today is that we have an equation for the voltage, and then of course the dynamics for the sodium channels and for the potassium channels depend on these gating variables that they are described by these differential equations here, which are the ones that I just discussed. Okay, and we have a system, a four-dimensional system of differential equations. Okay, that involve the voltage, three gating variables, and we want to study these equations using tools from dynamical systems. This is what we're going to do in the next session. Just to finish today, just let me mention these. Just recalling is that what happens is that we start with a value of the voltage, which is negative, okay? And then if, which is around here, okay? And for these values, we have that H is close to 1, while M and N are close to 0. So basically, this, since M is close to 0 and N is close to 0, these channels are closed. Okay. But then if due to a brief perturbation, we can increase the voltage, what happens is that now M increases. And what happens is that it increases very fast. So this means that this is not 0 anymore, but then the channels open. And then this term here, which is the sodium flowing in, the current, the sodium current, which is there the sodium ions flowing in. This is a negative current, so it goes with this negative sign. So this is positive. What it does, it makes the voltage to increase. Okay, and we are in this part here. But then what happens is that when the voltage increases, the potassium channels start to open. And then means that this is not 0 anymore. So then this involves this term here. And what happens is that now we have this potassium current that is an outward current. So this is positive with this negative sign. It produces the voltage to go back to decrease again. Okay, and then here, when the voltage decreases again, so all the channels close again, and we go back to the resting state. Okay, and we have the typical action potential shape. Okay? So here we have that the voltage increases, sodium channels activate, so M increases, sodium enters into the cell, this produces the voltage to increase even more, okay? But then sodium channels start to inactivate, so H decreases, goes back to 0, and at the same time, potassium channels activate. Potassium is an outward current, so it produces the voltage to decrease again, and it repolarizes the cell again back to its resting state. Okay. Here I put some, I just finished now. So here I put some movies that I found in YouTube that explain all this mechanism, but that I discussed today in a very nice movie. So you can look at it. And then what I'd like to do in the next session is to analyze this set of equations using tools from dynamical systems. We're going to do some reductions to reduce this 4-dimensional system to 2 dimensions, and then see what we can do with math. I don't know if there are questions.
Thank you very much. So you will send us the slides eventually?
Yes.
Okay, great.
What causes the sodium channels to open at the beginning? It's a brief depolarization, a brief change in the voltage that might be due to an external input that is basically an external current that the experimenter injects into the cell, or maybe it's due to other cells that are causing this change in the voltage. Okay, this is what we're going to talk about next session, is this property of this excitability that due to with a brief change in the voltage, this causes like this large excursion, okay, because the cell is excitable. I don't know if there are more questions.
I'm looking in the YouTube, so far no. Yes, it doesn't seem so. People can actually also ask questions if you have a microphone. Let me introduce, if there are no questions, let me introduce Pedro Maya. They works on, so I don't know if you met Pedro. Hello. Are you there?
Hello, I'm here.
Yes, so Pedro works also like you in modeling neural network, a different point of view. It's more data based, but I'm sure you share a lot of things in common. So,
okay.
Yeah, so I guess I'll ask, let's say a little bit more of a philosophical question then. I feel that today a lot of people from in machine learning are very interested in it's like in computational neuroscience due to the success of artificial neural networks on a variety of let's say kind of like machine learning problems. And so then I would ask you, I guess, like more philosophically, what do you think the biological brain has to teach the artificial neural networks, and what the artificial neural networks can teach us about the brain? That's like that.
Good question. I think that so artificial neural networks and these mechanisms of deep learning, they are capable to train a network to produce the output that you want. But the problem is that we still don't understand what are the mechanisms inside that are capable of producing this output. So they are sort of a black box in that sense. So we train the network. We can train the network to do whatever we want. It's amazing, actually. It's really powerful. But we don't understand how it does it. So the goal in computational neuroscience is like, we want to understand mechanisms. So we want to understand how, and we want to understand why the brain chooses this way, this strategy, this coding scheme. And I feel that in artificial neural networks, we don't want to understand how the network obtains this output and why it obtains it. It's more like we want the network to be capable to produce this output, but we don't care what I feel, even if I am not an expert on this, but we don't need to know the mechanisms that are hidden. And so for me, this is the big difference. It's like here we want to understand a little bit more about the how. Rather, this is my feeling.
There is a question, another question from the chat. Edmilson. Edmilson, you can ask if you want.
If you take a single cell experimentally and you isolate it, basically the perturbations is just basically this is an experiment that where you're going to inject, where the experimenter is going to inject current and is going to look at the properties of the cell, like the responses of the cell to this external input, just playing with this external input, like maybe changing the intensity, maybe making it changing in time, etc., and looking at the response of the cell to determine properties of the cell and what type of channels are involved, etc. So, yeah, if you take a cell and you don't provide any input, the cell is going to remain in the resting state.
We have more questions from Stephen Franklin.
Yeah, thanks. Hi. When you talked about the dynamics of the individual gates, you went from that sort of the mass action law to that statement involving the steady state and the time to steady state. Was that an approximation, or was that is there just a clear way of transforming between those two ways of looking at it?
Well, basically, it's like once you sorry. This is so to go for, you mean this step, right?
Yeah.
Yeah, this is typically using the form that of alpha and beta that Hodgkin and Huxley derivated. Then this is just a simple mathematical algebra that it turns out to look like this. Okay. But then to determine these values alpha, or these functions, alpha as a function of the voltage and beta as a function of the voltage, this is a very nice part of the work that Hodgkin and Huxley did, because they tried to estimate this experimentally, just clamping the cell at the different voltage values, and then trying to I mean, it's not direct, so they did a very intelligent, let's say, strategy to obtain this from what they could measure at that time. I don't know if this answers your question.
I think it does. Thank you. Yeah. So you're saying from the actual alpha and beta, you can convert it into this form.
Exactly.
Yeah. Thanks.
More question? Yes. Well, I guess if there are more questions, I don't see. If there are more questions, maybe there will be more questions next lecture.
Okay.
Thank you very much. I know it was very good, and I know it's very late for you. So thank you for making it possible at this well, for you, for Rodrigo, for Glaston in Polonia. I know that for Europe it's a little bit late, but try to adjust to a common background. Thank you so much. So
thank you.
Next, so if you send us so yes, let's clap the hand. Thank you, Stephen, too. So we can clap the hand.
Thank you. Thank you.
And
Maybe stop to record, Stefano.
yes, I have to stop to record. Okay. So next lecture will be on Thursday, same time, and I hope you're all coming back and to continue now to the more math part. Like, I'm really looking forward to bifurcation theory in this, and I want to stress that every mini course, the public is different, so that's good because target different people. So hopefully this will be very interesting and rich for everyone. So thank you, everyone, and see you next Thursday. So thank you, Jacqueline and Rodrigo, that are joined, and Umberto is not here. So thank you to everyone. Thank you to Gemma for this very
Thank
great
you. Thank you,
class.
and see you Thursday.
We are looking forward to see you Thursday. So thank you, Gemma.
Thank
And
you.
good night. I imagine that is, I don't know, 8 or 9 already.
8.
So see you
Okay.
all on Thursday.
See you.
See you. Bye.
Thank you. Bye-bye.
Bye-bye.